Welcome back to the deep dive, everyone. Today we're continuing our journey through Dr. Alok Aggarwal's groundbreaking book, The Fourth Industrial Revolution and 100 Years of AI. Last time we dug deep into the limitations of Moore's Law, the potential of quantum computing, and some of the hurdles it's facing.
Yeah, some pretty complex stuff. But today, we're really pushing the boundaries even further beyond silicon.
Wow, beyond silicon. We're exploring a future of computing that might completely reinvent how we process information. We'll explore groundbreaking alternatives like optical and graphene-based computing, dive into neuromorphic systems, and even look at DNA as a potential storage medium. Plus, we'll unpack the latest specialized processors designed to supercharge AI training and inference. A glimpse into the future of computation.
So, as we discussed, silicon-based computing is really struggling to keep up with, this exponential growth in demand for computing power. Moore's Law, which predicted the doubling of transistors on a microchip every 2 years, it's hitting its physical limits. We simply can't cram transistors onto a chip forever, right?
It's only going to get harder. The demand for processing power is only going to increase, right? With the rise of AI, big data, these complex simulations. So where do we go from here?
Well, one path leads us to the realm of light, specifically to optical computing. So, instead of electrons, optical computing harnesses photons, particles of light for computation.
Okay, I'm already intrigued. Light travels incredibly fast, but how does it actually compute?
So think about how data is already transmitted through fiber optic cables. Electronic signals are converted into pulses of light, which allows for incredibly fast data transfer. Optical computing kind of takes this concept further by using photons to perform calculations within the computer itself.
So are we talking about replacing the entire computer architecture with optical components? That would be incredibly complex.
It definitely is a huge undertaking, and one of the main challenges lies in building optical CPUs, creating optical transistors and logic gates that can manipulate photons the way we manipulate electrons. It's no easy feat. But researchers are exploring the potential of nonlinear optics, a field that focuses on how light interacts with certain materials to try and overcome these challenges.
So instead of relying on the flow of electrons, we're essentially trying to control the behavior of light itself. Fascinating. But what's the real payoff here? Is it just about speed?
Well, speed is a major advantage for sure. Optical computers could be at least 1,000 times faster than our current computers, potentially allowing us to process information at the speed of light. But it goes beyond just speed, right? Because photons don't generate heat like electrons do, meaning optical computers would be significantly more energy efficient, and they'd also be less susceptible to electromagnetic interference.
That's remarkable. Imagine a world where downloading an entire library takes, seconds instead of hours. It almost feels like we're talking about a different dimension of computing altogether. But what about something a little more down to earth? Perhaps literally. I've heard whispers about graphene and its potential in computing.
Graphene, the wonder material. It's a single layer of carbon atoms arranged in a honeycomb lattice, and its properties are truly remarkable. We're talking stronger than steel, lighter than aluminum, incredibly flexible, and an exceptional conductor of electricity.
Okay, those are some impressive stats. But how does a single layer of carbon atoms translate into a better computer?
It all comes down to its conductivity. Graphene's unique structure allows electrons to move through it with incredible ease, making it, ideal for building transistors. The fundamental building blocks of modern electronics.
So could we be looking at a future where graphene transistors replace silicon ones?
That's definitely a possibility.
Okay. However, there have been challenges in manufacturing graphene transistors with the consistency and purity required for large-scale production. You see, defects in the graphene structure can impact performance.
Right, I see.
But researchers are making significant strides in overcoming these obstacles. In fact, a team recently built a 16-bit microprocessor called the RV16X Nano with 14,702 carbon nanotube transistors.
Whoa, that feels like a major breakthrough. What does this mean for the future of devices?
Well, imagine incredibly powerful yet flexible electronics. Think foldable phones that don't sacrifice performance, wearable devices woven into fabrics, or even lightweight, super efficient spacecraft components. Graphene really opens up a world of possibilities for flexible, high-performance electronics.
We've explored computing at the speed of light and the potential of a wonder material. What other revolutionary ideas are brewing in this world of computing?
How about storing the world's data in DNA?
Wait, did you say DNA? As in the blueprint of life itself?
Yeah, DNA.
It might sound like science fiction, but the concept is really rooted in DNA's incredible information density.
Oh, wow.
Right. So imagine using synthetic DNA with its 4-letter code of C, G, A, and T to store digital information. So a single gram of DNA could theoretically hold the equivalent of 215 million gigabytes of data.
That's mind-boggling. We're talking about storing entire libraries in this space, smaller than a grain of rice.
It is, yeah.
But how do you actually write data onto DNA and then retrieve it?
It involves a complex process of translating digital data into sequences of DNA letters, synthesizing that DNA, and then using DNA sequencing technology to read the data back. It's still early days for DNA storage, but the potential is enormous. Imagine a world where we archive information for millennia in incredibly compact and durable DNA molecules.
We've gone from light to carbon to the very essence of life itself in this quest to redefine computing. What could possibly top that?
Well, how about mimicking the most complex organ we know of, the human brain? That's the driving force behind neuromorphic computing.
Okay, you're not talking about traditional AI, are you?
It's something even more radical. Neuromorphic computing aims to replicate the structure and function of the human brain in hardware, building computers that work like brains, not just simulate them.
So instead of programming computers, we're essentially trying to grow them. I can't even wrap my head around that. But what are the potential benefits?
Think about the incredible efficiency of the human brain. It excels at complex tasks, pattern recognition, problem solving, all while using very little energy. Neuromorphic computing aims to replicate those capabilities in hardware, potentially leading to AI systems that are far more efficient, adaptable, and perhaps even capable of learning and evolving like biological brains.
This is truly pushing the boundaries of what we thought was possible in computing. We've covered optical computing, graphene, DNA storage, and now neuromorphic technology. It feels like we've taken a giant leap into the future.
These technologies aren't just theoretical concepts. They have the potential to revolutionize everything from artificial intelligence and medicine to data storage and even space exploration.
Absolutely. We've been looking at cutting-edge computing technologies, but here's the reality check. Quantum, optical, and graphene-based computing are still finding their footing. So scientists have been doing something incredibly pragmatic, developing specialized processors designed to supercharge AI training. We're talking about hardware specifically engineered to make AI model training more efficient, less expensive, and dramatically more energy conscious.
Indeed.
Yeah. And I think this is going to be really interesting because, I remember when I first started learning about AI, I was like, wait a minute, the things that make those crazy video game graphics are the same things that are now training AI. That's kind of wild.
It is really wild. It's really fascinating how these different fields kind of come together and you find these innovations in one place and they end up being really useful in a completely different place.
Totally. And what's the story there? Like, how did these GPUs... They were designed for gaming, right?
Yeah, so they were designed by NVIDIA back in 1999, and the goal was to revolutionize gaming graphics, make things faster, smoother, more realistic, all of that. And the way they did that was by focusing on parallel processing. So instead of having one processor that does everything, you have a whole bunch of smaller processors that can work on different parts of the problem at the same time. And that turned out to be a really good fit for the kind of calculations that you need to do for an AI.
Okay. So help me understand this a little bit better. Like, what is it about parallel processing that makes it so much better for AI than just having one big, powerful processor?
Well, think about it like this. If you're training a neural network to recognize cats in images, you need to feed it tons and tons of examples. And each image has millions of pixels, and each pixel needs to be analyzed and processed. And all of that requires a lot of calculations.
Okay.
Now, a CPU like the one in your laptop, it's really good at doing one thing at a time. It's like a master chef that can cook any dish, but they can only cook one dish at a time. But a GPU, it's more like having a whole kitchen staff. So you have somebody chopping vegetables, somebody stirring the sauce, somebody baking the bread, all at the same time.
Okay, that makes a lot more sense.
Yeah, and that's what makes it so much faster for AI training. They can handle these massive amounts of data and do all these calculations in parallel.
I see. And so is it just the sheer number of calculations, or is there something else about the way that GPUs are designed that makes them particularly well suited for AI?
Well, there are a few key things. First of all, they have a lot more cores than CPUs, so that means they can do a lot more calculations per cycle. They also have much higher memory bandwidth, so they can move data around much faster.
Makes sense.
And their memory access time is much lower, so they can access the data they need much quicker.
Wow. Okay, so it's like a combination of all these factors coming together.
Exactly. Yeah.
And so that's why they're just so much faster.
Exactly. And speed is really important in AI because the faster you can train your models, the faster you can iterate and experiment and try new things and make progress.
Yeah. And isn't it true that sometimes you have to train these AI models for days or even weeks at a time?
Oh, yeah, absolutely. And some of the really big models can take months to train. So any speed up you can get is a huge win.
So I guess what I'm getting at is that, GPUs are like the marathon runners of the computing world. They're built for endurance and handling these massive data sets.
Yeah, that's a good analogy.
But I know that they're not always the perfect tool for the job.
Right?
Are there any specific scenarios where they're like the undisputed champions?
Yeah, there are definitely some things that GPUs are really good at. So if your problem can be broken down into a bunch of smaller steps that can be done in parallel, and if it involves a lot of repetitive calculations on regular data like images or matrices, and if it needs to move large chunks of data around, and if it doesn't need to be super precise in every single calculation.
Okay, so they're not exactly precision surgeons, but they're phenomenally handling the heavy lifting.
Yeah, exactly.
And wasn't there a specific moment in time when people kind of realized that, oh my gosh, these gaming chips are actually AI powerhouses?
Yes. There was a really pivotal moment back in 2012. There's this competition called the ImageNet Challenge. And it's like a prestigious computer vision competition. This team of researchers, they used GPUs to power their model, which was called AlexNet, and they just blew the competition out of the water. It was a really big deal because it showed the world that GPUs could be used to train deep learning models and do it really well.
So it was like a grand unveiling. Everyone's like, hey, these gaming chips are actually secret weapons for AI.
Exactly. Yeah. It was a real turning point.
And so did that just spark this whole wave of innovation and research in GPUs for AI?
Oh, absolutely. It kicked off a decade of incredible progress in deep learning. People started using GPUs to train bigger and better models and tackle all sorts of problems that were previously thought to be impossible.
So it's kind of like GPUs became synonymous with AI?
Yeah, pretty much.
Wow, that's amazing. And so, but the world of AI hardware doesn't stand still. Did anyone try to challenge the dominance of GPUs?
Oh, absolutely, yeah. Other companies started to develop their own specialized processors, and one of the most interesting contenders came from Google.
Okay, I feel like it's going to be a good story. What did Google do?
So they created their own chip called the Tensor Processing Unit, or TPU for short. And unlike GPUs, which can handle a variety of tasks, TPUs are laser-focused on deep learning.
So they're like the specialists, the brain surgeons of the AI world.
Yeah, you could say that. And they were incredibly powerful too, way faster than GPUs.
Really? How much faster are we talking about here?
Well, there is a study that found that the performance gains from TPUs were equivalent to skipping 7 years of Moore's Law.
What, 7 years?
Yeah, it's pretty crazy. And their second-generation TPU, which came out in 2017, was 8 times faster than the leading GPUs at the time.
8 times faster? That's just mind-blowing. It's like comparing, a horse-drawn carriage to a supersonic jet.
Yeah, it's a huge difference.
Wow. Okay, so Google really came out swinging, but they weren't the only ones pushing the boundaries, right?
No. There were other companies working on different approaches. And another one that's really interesting is FPGAs, or field programmable gate arrays.
Okay, I've heard of those, but I don't really understand what they are.
So they're kind of like ASICs, which are application-specific integrated circuits. So they're chips that are designed for a very specific task. But the cool thing about FPGA is that you can actually program the hardware after it's been manufactured.
Well, you could reprogram the hardware, so it's like having a chip that can morph and adapt to different tasks.
Exactly. Yeah, it makes them really versatile.
Wow. Okay, that's pretty wild. So when were these FPGAs invented?
Well, the concept actually goes back to the 1960s. But it's really in the past decade or so that they've started to gain traction.
I see. And are they being used for AI stuff?
Yeah, definitely. There are companies like Microsoft that are using them to speed up things like search engines. And Xilinx, which is one of the leading FPGA companies, they're using them in healthcare for all sorts of things like analyzing ECGs and MRI and CT scans and even endoscopy.
Oh, wow. So they're popping up everywhere. And even Tesla is using them in their self-driving cars, right?
Yeah, they have their own custom chip called the D1 Dojo. And it's specifically designed to handle the massive amounts of visual data that they need to train their self-driving algorithms.
So FPGAs are like the ninjas of the computing world, quick and agile and adaptable. But I feel like there's got to be a trade-off, right? Like they can't be perfect for everything.
You're right. One of the downsides of FPGAs is that they require specialized programming knowledge to configure them.
Okay. So it's not as simple as just plugging them in and running your code.
Right? You need to have people who know how to work with the hardware, and that can be expensive.
So it's a trade-off. More power and flexibility, but with a bit more effort required.
Exactly. But for some applications, it's definitely worth it.
I see. So far we've seen this incredible evolution from general-purpose CPUs to these specialized processors like GPUs to be used in FPGAs. And it's like everyone's trying to push the boundaries of what's possible in AI.
Yeah, it's a really exciting time to be working in this field.
It is. But where does it all lead? Are we on the cusp of something even more revolutionary?
Well, that's a great question, and it's something that researchers are actively thinking about because while these specialized processors have been amazing, they also present some challenges.
Okay. Like, what kind of challenges are we talking about?
Well, imagine a future where we have tons of different specialized processors, each one optimized for a very specific task.
Okay.
It could get really complicated to manage all of that.
Yeah, I can see that. It's like solving one problem, but potentially creating another.
Exactly. We could end up with a very fragmented landscape where every AI application needs its own unique hardware.
And that would make it really hard to develop new applications and share code and collaborate with other researchers.
Exactly. So, one of the big questions is how do we harness the power of specialization while also maintaining some level of standardization?
That's a really interesting question, and I guess it kind of leads us to another question, which is there a way to develop a standardized training model that can work across all these different hardware platforms?
Yeah, that would be ideal because then you could just switch out the hardware depending on what's available or what's most efficient for a particular task.
Right, that would be a game changer.
It would, and it's something that people are working on.
Okay, it sounds like the future of AI hardware is still very much up in the air. There are a lot of exciting possibilities, and it's going to be fascinating to see how things develop in the coming years.
So we've got these specialized chips for training AI algorithms. But there's another side to this, making predictions or inferences with trained models. What's happening there?
Well, once an AI algorithm is trained, using it to make predictions or inferences can often be done with much less powerful hardware.
That makes sense. So are we talking about smaller, more energy-efficient chips for this stage?
Exactly. And this is crucial for applications where size and power consumption are limited, like smartphones, cameras, and sensors. Imagine a traffic camera that can detect pedestrians in an intersection without needing to send all that video data to a central server for processing.
Wait, is that a real thing? A traffic camera that can make decisions on its own?
Absolutely. It's an example from Dr. Alok Aggarwal's book, and he explains how specialized hardware is enabling these kinds of real-time AI applications in everyday devices.
So we're not just changing the materials we use for computers, we're also completely rethinking how they're designed and used. It's like we're entering a whole new era of computing.
It really is. And this is where things get really interesting because, with the rise of specialized hardware, we're seeing a shift away from the one-size-fits-all approach to computing and towards a more modular, adaptable model. It's like we're moving from a world of monolithic supercomputers to a world of interconnected, specialized devices, each with its own unique capabilities.
And this is happening on both the training and inference sides of AI.
Precisely. We've got specialized chips for training AI models, smaller and more efficient chips for making predictions, and even FPGAs, which can be reconfigured to handle a wide range of tasks. It's like the whole landscape of computing is being rewritten right before our eyes.
This is also fascinating, but I have to admit it's a lot to take in. Can we take a step back and try to make sense of all these different pieces?
Yeah, there's this whole other area of AI inference happening after you've trained an AI model. It's where that AI actually gets put to work, making decisions and predictions based on all the data it's learned.
So it's like you've got this big brain of specialized training chips doing all the heavy lifting, teaching the AI everything it needs to know. And then you need a different set of tools for actually sending that AI out into the real world to do its thing.
Exactly. And Dr. Aggarwal makes this distinction in his book. He talks about how there are essentially two types of specialized processors emerging for AI inference: mid-range and low-range.
I'm intrigued. What's the difference?
Well, mid-range chips are being used in things like robots, drones, industrial sensors, and applications that might have a decent amount of power available, but still can't afford to get too hot. We're talking about chips that operate in the 3 to 20 watt range, roughly.
So not something you'd find in your smartphone, but maybe something powering a self-driving delivery bot or a really complex factory automation system.
Exactly. They need to be powerful enough to handle complex AI tasks in real time, but they also need to be energy efficient and relatively small. Then you've got the low-range processors operating under 3 watts. These are designed for things like smartphones, wearables, even those smart earbuds that react to what's going on around you.
Wow. So we're talking about AI being embedded in pretty much every aspect of our lives, making decisions and taking actions in the background without us even realizing it.
That's where things are headed with low-range inference chips. Battery life is a huge concern, but they still need to have enough computational power to make smart AI decisions right there on the device itself. Think about a medical device that can monitor your vital signs and alert you to potential health problems before you even notice any symptoms.
It's like having a tiny doctor on call 24/7. That's incredible. So we've got these specialized chips for training AI models, and then smaller ones for making predictions, and they're all getting smaller, more efficient, and more specialized all the time. But is that the whole story on the hardware front? Are there any other surprises in store?
There's always something else, right? Dr. Aggarwal actually points out something interesting. While there's a lot of buzz around using CPUs, GPUs, even Google's TPUs for AI training, FPGAs might have a hidden advantage, especially in the long run when it comes to inference tasks.
Okay, refresh my memory. What are FPGAs again?
Field programmable gate arrays. Essentially, they're chips that you can reconfigure after they've been manufactured, which gives them incredible flexibility. The downside is that they're a little trickier to program. They require some specialized expertise. But once you get it right, they can be incredibly efficient for specific tasks.
So instead of having a chip that's designed for one specific job, it's more like a chip that can handle many different jobs. But you need a specialist to reconfigure it each time.
And for AI inference, where speed and cost are super important, that flexibility could make FPGAs a really dominant force, even though it's still early days.
It's amazing to think about how much innovation is happening in this field. This deep dive has been a real eye-opener. We've covered optical and graphene-based computing, DNA storage, neuromorphic computing, and the rise of specialized hardware for training AI algorithms and making real-time predictions. It's a lot to absorb, but it's clear that the future of computing is going to be unlike anything we've ever seen before.
It certainly is. And this is just the beginning. In our next episode, we'll shift gears a bit and explore the fascinating intersection of demographics, technology, and the future of work. We'll discuss the impact of the world's aging population and the slowdown in population growth, as well as the potential for both job losses and job creation due to AI, robotics, and automation. It's a complex and incredibly important topic that we'll be examining from multiple angles.
That sounds fascinating. I'm really looking for that discussion. Until next time, keep those minds curious and those imaginations running wild.
See you next time.